Hi, my name is Caitlin Candell. This is my combined spectral problem, organic chemistry project. So in order to solve for this and find out what compound we have for C7H14O2, we're going to first start off with determining our degree of unsaturation. To do this, we are going to multiply the amount of carbons by 2. We're going to add 2 to that and then subtract our hydrogens. So we'll have 16 minus 14, and then we're going to divide that by 2. So 2 divided by 2 is going to equal 1. This is going to tell us that we're going to have one double bond or one ring, cyclohexane ring, in our compound. So this could be a carbon-to-carbon double bond or carbon-to-oxygen double bond. Next, we're going to look at the IR spectra. So when we're looking at this, we're going to see that we have peaks around 1,000 to 1,200, but multiple here. Those are going to be consistent with your carbon bonded to an oxygen within a single bond. And then at 1740, this is a classic C carbon double bonded to an oxygen. And then here we have a 2850 and 2980. We see peaks that indicate a sp3 hybridized carbon hydrogen stretch. So our structure contains 2 oxygen atoms, so the IR spectra is consistent with the potential for a double bond right here, and then with a carbon also bonded to an oxygen over here. So we're thinking now, instead of a carbon-to-carbon or having a cyclohexane or some sort of ring, we're probably going to have a double bonded carbon to an oxygen. The absence of a wide hump here at 3300 would rule out an alcohol or carboxylic acid. So now we'll move down to the carbon spectra. On this, we're going to see peaks at 173-ish, 60, 42, 22, and 23, and then again probably at 17. So these are all going to indicate different orientations of our carbons. At 173, this is most consistent with a carbonyl carbon, which you'll see around here on this over here at the chemical shift. The shift at 60 is going to be consistent with your carbon bonded to an oxygen with a single bond. And then the lower than 40 is going to be your hybridized carbons. So we're going to see a shift at around 21, 22, 23 area, and then around 17. This 17 is going to indicate our terminal carbon, our CH3 methyl group. And these are going to indicate just some sort of internal CH2 carbon. All right, so now we're going to look at our hydrogen spectra. And we're going to see 5 shifts. We're going to be looking at the integration, multiplicity, and what those indicate. So the first one we'll talk about is this 4.1, where you'll see 4 peaks here, and those are going to indicate that it's a quartet. If we go down the line, we're going to see that we have a 2.3, which will be a doublet. This 2.1 will be a multiplet, 1.2 a triplet, and then this 0.9 is going to be a doublet. This 0.9 is going to be most consistent with a carbon that's bonded to 2 methyl groups. This 1.2 will be a single bonded oxygen to a CH2-CH3 group. And you're going to see that that's going to be integrated with 3 hydrogens. And this one will be integrated with 6 hydrogens because we think that it'll be a carbon bonded to 2 methyl groups. At the 2.1 mark, we're looking at a carbon that also has 2 methyl groups. So that could be similar to this one, just a carbon that's already in that same chain. And this 2.3 is going to be a doublet integrated with 2 hydrogens, and that is going to be our double bond that we're looking for. So our carbon bond to double bonded to an oxygen. So CH2C double bond oxygen. All the way down at this 4.1, This will be our single bonded oxygen to the CH2. All right, so now we're going to review all of the items we just went over, all of our different bond arrangements. And I do want to point out that this, on this carbon spectra, our 173 does show us our double bonded oxygen, but also shows that our carbon is bonded to an oxygen. So we need to keep that in mind when we are drawing our compound. So let's try and draw it. So we know that we're going to have that carbon. It's going to be bonded, double bonded to an oxygen. We know now that that's bonded to an oxygen. We have that our O oxygen is going to be a CH2 to CH3. That's an oxygen. So CH2, CH3. And then we know that we have a terminal CH3. And we're going to have on the other side of this carbon a CH2, a C, CH3, and or CH and a C, two CH3s. So that should equal 1, 2, 3, 4, 5, 6, 7 carbons. It should be 3, 5, 6, 7, 8, and then 6 hydrogens, so 14 hydrogens, and we've got 2 oxygens. We scroll down here, we'll be able to see a cleaned up version of it, and this is our structure, ethyl isovalerate.